as I hope you got my email, problem set 6, I'm not going to get to through enough material to be sure I've covered all the bases for problem set 6 by Friday. So the next reasonable time to have it due is a week from Friday. So I'm sure that's another hardship. I'm making you wait another week and a half to have it due. By then we'll have gotten deep into and beyond airplanes, so it should be easy peasy, or at least you have the opportunity you have the background to do all the questions. All right? So problem set 6 is now due November 2nd. The other thing, there was one other thing. Oh, I've gotten a little behind in the lecture videos. I have filmed the lecture video for today, but I haven't finished editing it to post it. So it's going to go up this afternoon, and I apologize for that one too. It's life. Any questions, issues about the class outside of the content? Okay. For today, I really hope to just cover all of garden watering and really set the stage for what that is. So working with water, we already talked about working with water in terms of plumbing in your house. Hopefully you've got a decent understanding of how water flows around from the water company through the plumbing into your house. In doing that, in that story, the story of water distribution, I assumed a few simplifications. First off, we sort of concentrated on steady state flow that wasn't starting or stopping, that was actually underway, and basically you couldn't see anything happening other than yeah, there's fluid moving through the system, but the environment's not moving, so it can't do work on or negative work on the fluid, and the fluid is flowing so steadily you can't even observe the passage of time in it. Makes life simple. So that was steady state flow, and the other thing about steady state flow is that it's typically the assumption is made, and I made it, that there's no viscosity to the fluid. The fluids flow perfectly. So just to sort of reiterate the story as it stands in the world of water distribution, flows are perfect, very simple. There's no rubbing, no friction-like effects. And so the ordered energy that you have when you start, and by ordered energy, in case I haven't emphasized, this is energy that could do work. So not thermal energy, which is disordered energy. It can't directly do work. It is not equivalent to work. The ordered energies were gravitational potential energy, kinetic energy, and pressure potential energy. And the water flowing through one of these beautiful stationary systems, steady state flow, the energy just goes back and forth between those three forms of energy, of ordered energy, as it flows along a streamline. All right? And that allowed us to watch it go through the plumbing. I hope just for public service announcement things, the reason why, if you've got a building that is fed by the same plumbing from the water company, but is multi-story, the situation is different. In the bathrooms, for example, taking a shower in the different floors, I hope you now understand why and realize that it's true, that as you go up higher and higher in the floors, the showers get weaker and weaker. The stream of water that comes out of the shower gets weaker because more of the energy is tied up as gravitational potential energy as you go to the upper stories. There's less available to be either pressure potential energy before the nozzle or kinetic energy after the nozzle. So I imagine that's somewhat familiar to you guys. In fact, by the time you go to skyscrapers, and this is sort of public service announcement stuff too, skyscrapers cannot operate with simple plumbing. You can't just have one water line feed the entire 20, 50, 100 floors because there's such a huge range of gravitational potential energy on the different floors that if you used one pipe and you gave the water enough energy per drop to reach the 100th floor at all, that's a lot of gravitational potential energy per drop. You'd have to pump hard to get it that high. The shower up there would be maybe tolerable because the water would still have a little bit of pressure potential energy to become kinetic energy. But down on the first floor, people would get holes drilled in them because the water would have so much energy available, not as gravitational potential energy down there, but rather as tremendous pressure potential energy or tremendous kinetic energy. So skyscrapers have a very complex plumbing system. They have to. fighting fires on high rise is very complicated as well, because to get the water up that high, you have to give it a lot of energy per drop. So you use big pumps. Skyscrapers typically are built with water tanks in them at the top, and if there is a fire, they immediately begin moving as much water as they can up as high as they can, as quickly as they can, because if you're going to be fighting it, you want to fight it with high energy water that can reach the upper stories. All right? So, okay, having gotten that far, now we're going to go into the world of garden watering. This is my excuse for talking about the things that I swept under the rug to this point. One of them is viscosity. The fact that water doesn't flow perfectly past itself. So I'll talk about that in a minute. It rubs, it wastes energy. And another thing is that when water starts to turn, when it bends, or any fluid is flowing and it bends, it's got to be pushed to the side. Something's got to exert forces on it. And in the middle of a flow of water, the middle of a stream, for example, the only thing that's touching the water is the water. The water to its left, to its right, above it, below it, it gets pushed on by the water in order to go around that bend. And so the water has to develop a pressure gradient to push on it, to push it to the side. And it does develop a pressure gradient. So there are weird pressures that start showing up when water flows around turns and air flows around turns. And the last thing I'll talk about is that not all flow is perfect and smooth. I've talked to this point about water flow that it is what's called laminar. It just goes beautifully through a system, and it has streamlines, which is to say you can follow water that began at a certain spot and follow it all the way through the system, and every drop that passes the initial spot will follow the same path. And you can put drops of ink in that water, and you watch the drop of ink work its way through the system, and it maps out the streamline. And every drop of ink you put at that same starting point will follow the same streamline all the way to the end. Very simple. That's the world of laminar flow, but it's not everything. There's also what's known as turbulent flow and stuff in between laminar and turbulent. Turbulent is white water. It's a swirling, messy stuff. If you watch a lazy river flowing along, it's typically laminar up until it rolls across a whole bunch of rocks, and then white water, turbulent. Okay? Question on midterm. It's still Monday, a week from today, October 29th. Yeah, Sophie?
Will it all focus on the material since the first exam?
This midterm, the second midterm, will concentrate to a large extent on material since the first exam. So what did we get to? We were somewhere in carousels and roller coasters. And so it'll emphasize that, but it will also reach back into the old stuff. Okay? So don't count on it don't forget bouncing balls. All right? Any other questions like that? Yeah, Sam?
When you say it'll reach back, will it build on that, or will it just have a few questions?
It will build on way back. Everything builds on everything to some extent. It keeps showing up, like go around a turn, you need a force to go toward the inside of the turn. I mean, we're back in carousels by accident here, looking at water flowing through a pipe. But I will ask some just questions right out from how a ramp works. Still there. Other ones? Yeah, proud. Well, I will probably get slightly into airplanes, how airplanes fly on Friday. That's my hope. All right. So we'll probably have. There may be a question or two about how does a wing support a plane. Okay. Well, yeah. All right. So viscosity. First thing about the complexities of fluids. They don't flow perfectly. They don't flow perfectly even past themselves, which is to say if you've got two layers of water, so you're in the middle of a stream, and for some reason one layer of water in this stream, let's make it motionless just so it's really simple. The water is sitting still and another layer next to it. Don't worry about how thick the layers are. The details, not important. The second layer of water is moving past it. And the only things that are touching in this story are water and water, and yet they exert forces on each other. And those forces are called viscous forces, and they're kind of like sliding friction to an extent. They are trying to bring the two portions of fluid, the two layers, to the same velocity. So if one's stationary and the other's moving, the stationary one wants to stop, tries to stop the moving one. And the moving one tries to get the stationary one moving with it. And they compromise, to some extent, but they're rubbing across each other. They exert forces. Negative work ultimately is done somewhere in the system, just like with sliding friction, and energy disappears. It becomes thermal energy. It's not totally destroyed. So this is the notion of viscosity, that layers of fluid sliding across each other rub and exert forces on each other, waste energy. We'll see how they influence things going forward. The notion of viscosity. Viscosity is a physical quantity that characterizes a fluid. So any given fluid has a viscosity. That's a little. Finally, when you really look in the details, life gets complicated. But for most part, for our purposes, fluids have a single viscosity. Life is simple. Water has a certain viscosity, which is the extent to which layers rub against each other when they're in relative motion. And that viscosity characterizes water. It's different from the viscosity of honey, for example. Honey has a much higher viscosity. Air, another fluid, has a viscosity. It's way smaller than the viscosity of water, but it's not zero. Air, as it goes across air, rubs. One issue about these viscous forces that's different from the world of normal friction. Sliding friction, when you slide an object across, if I slide this across the table, we're experiencing sliding friction. It doesn't matter whether I slide slowly or I slide fast. The forces of sliding friction are typically one value, give or take a little bit. Doesn't matter how fast the sliding is occurring. That's not true of viscosity. The forces between two layers of water that are rubbing, the force is almost proportional to how fast they're going across each other. So the faster you go, the more you rub, the harder the rubbing gets. And that will have influence on the way the world works. Okay, so fluids, sliding across fluids, rub. Waste energy, tend to try to go to the same velocity and so on. Any questions about viscosity, the idea? You sort of just watch all the things, the fluids you play with, oil, shampoo, all that stuff. They're all, you can sort of see different syrupinesses to the different things. Okay. How does that affect the water in a pipe? So up until now, I've talked about water in pipes in the plumbing in your house for water distribution. Now let's go out in the yard with a hose, just so we can move more. And the water flowing in a hose rubs against the hose itself, and then the water rubs against the water. The story is this, that the water that touches the surface of the pipe on the inside, or the inside of a hose, that water is viewed as being motionless. And, this is one of these things that the physicists try to figure out how to describe that that last layer of water right there on the hose's surface or the pipe's surface, touching the hose or pipe. What's the speed of that water? And the general consensus is that it's motionless. So there's a layer. Think of the outermost layer of water inside a hose as not moving at all, just sitting on the surface of the hose. All right? Is that a friction or something? It's kind of like a friction issue. It's stuck there you can think of it as static friction. It's stuck. Well, that has a huge influence on the rest of the water flow, because if that outermost layer of water is motionless, then it affects the layer next to it. They're rubbing. So as I was doing the lecture video, to identify layers, think of that outermost layer of water. We haven't defined how thick it is. It just doesn't matter. Let's call it layer 0. And then it's the one that's not moving. And then the layer just adjacent to it, heading into the middle of the pipe. That's layer 1, and then layer 2 is next to that, and layer 3. Well, layer 1 is sliding across the motionless layer 0. And that slows down layer 1. Therefore, layer 2 slides across layer 1. And layer 3 slides across layer 2, and so on. They're all rubbing all the way to the center of the pipe. And that rubbing effect slows down the water to different extents. The water that's closest to the walls of the pipe or hose travels the slowest, because ultimately its forward speed has to be 0 when it gets all the way to the wall of the hose. And as you come in, it can go a little bit faster than 0, but not a lot. And as you get farther and farther from the wall and deeper into the middle of the pipe, you can go faster. So the water flow inside a pipe, finally, when the dust settles, if you've got a pipe or hose, and I'm cavalierly flitting back and forth between the two words, and I don't even know what the difference is between them really. Just let's have a nice long straight line of hose or pipe. Water is not going to coast through that hose. In the absence of viscosity, it would. It would go right through, just like an object in deep space would just coast forward with no force. It doesn't coast because of this rubbing effect, any more than the stick coasts because of sliding friction. It's sort of the same idea. If you don't push it, an object comes to rest here on the surface of the table because of friction effects. In the water, if you don't push the water forward, it comes to rest because of friction-like viscous effects. All right? So you got to keep pushing. So to get water through a hose, you got to keep pushing to keep it going. And how do you push on a fluid? Well, you push on it with forget gravity, let's work horizontally, so gravity's not the pusher. Let's use pressure. A difference in pressure pushes water through a hose. So if you have high pressure at the start, low pressure at the end, that difference in pressure pushes the water forward and keeps it moving against the slowing effects of viscosity. And it turns out that the amount of water that goes through a certain hose, so just imagine a hose just lying there, and let's make it straight for reasons we'll come to later, nice and straight. And to keep the water chugging through that hose, you have to have a pressure difference, and the amount of water that goes through that hose is going to be, it turns out, is approximately proportional to the pressure difference. So if upstream you have 2 atmospheres of pressure, that is normal ambient atmospheric pressure plus an additional atmosphere of pressure, which you made with a pump. And at the end, you have only atmospheric pressure, just the ordinary air. That's a 1 atmosphere pressure difference between start and finish. That's a certain push, and you'll get a certain amount of water through. If you double the pressure difference by cranking up the starting pressure by yet another atmosphere, you get twice as much water through. This is just an observation, and it's pretty close to right. Okay, so push harder, you get more water, and it's essentially proportional to push. Another thing you can do is if you change the length of the hose or pipe, you're changing the distance over which that pressure difference is acting. You're also changing the distance over which the viscous slowing effects are acting. And it turns out if you double the length of the hose, you get about half as much water through. You're doubling the distance over which the viscous forces are slowing the water down. You're making the same pressure difference do the push. So you get less water through as the hose gets longer. And it's pretty much proportional. The amount of water that gets through is pretty much proportional to 1 over the length. Okay? Hopefully that's sort of common sense. It turns out to be about right. Or it's intuitive. Third possible thing is if you instead of using water, you use something that's more viscous, like honey. Now you get a lot less honey through than you get water. And it turns out that the more viscosity, and viscosity is a measurable quantity, and it has units which we'll set aside. If you double the viscosity of the fluid you're shoving through the hose, you have the amount, you divide by 2 the amount of fluid you get through. It's also kind of the first thing you would guess. Okay, more viscosity, you get more trouble. It's harder to get the stuff through. This explains, for example, why when you try to get honey out of the tap at the natural food store, it doesn't come out very fast, even though they might be pushing pretty hard. It's slow through the pipes. Peanut butter is probably even worse. Okay? Fourth thing that affects the flow of fluid through a pipe or a hose is the diameter or alternatively radius. I'm going to just stick with diameter just for simplicity. diameter is twice the radius, right? I got all tied up in my words. So if you double the diameter of the pipe, how will that affect the amount of water that goes through? And you might think it's maybe a factor of 2 or a factor of 4. It turns out it's a factor of 16. Doubling the diameter of the pipe makes a huge difference in how much water goes through. For reasons that, there's several reasons why it has this effect and why they're cumulative. First off, if you double the diameter of a pipe from this diameter to twice that diameter, the opening increases by a factor of 4. If you slice the pipe, it's a circle. And the circle has a surface area that's proportional to the square of the diameter. You did this in geometry somewhere way back. Pi r squared and stuff like that. So doubling the diameter of the pipe gives you more room by a big factor, factor 4. The other thing is it gets the water at the center of the pipe farther away from the walls by a factor of 2, and that's another huge effect. Because remember, the water is slows down a lot near the walls, and it's actually traveling faster through a pipe near the center than it is near the walls. And so most of the water, most of the water that is delivered in the central core of the pipe. So make that core bigger and farther from the walls, it can move faster. And that's another factor of the diameter squared that shows up in that calculation. So overall, when you double the diameter of the pipe, you get 16 times as much water through, leaving everything else the same, which means same length, same pressure difference, and you're using the same viscosity fluid, water. So public service announcement piece of this is someday maybe you'll have a yard, or maybe you already do, and you want to go get a hose to water the yard and so on. You go to the hardware store, and you're often presented with a couple of different choices for the diameter of the hose, the internal diameter, the one that matters. And the two classics are 5/8 of an inch and 3/4 of an inch. Those are very popular sizes. And that just doesn't sound like any difference at all. In fact, you'd have to get out a ruler to be sure you've got one versus the other. 5/8 of an inch, 3/4 of an inch is 6/8. That's 5/8 versus 6/8. What's the difference? Nothing. It's a factor of 2 in water delivery, because you square that. You raise that diameter to the 4th power. It's a big effect. And I can show you that effect. Okay, so to do this, I have to dim the lights and then zoom the camera in. So we look at that tank of water, and I can put in a little hose. So the water's pressure is going to come from the height of water above the opening here. This is at atmospheric pressure here, and as you go into the water, the weight of the water overhead pressurizes it. So the pressure here is I could calculate it, but it's a tiny bit over atmospheric pressure. And I'm going to go through I'll use this one. This is 1.25 millimeters in diameter. I've got a plug in here so that we can keep the water from flowing out too fast. Okay, so can you see the water dripping out of there? That's how fast this pressure difference between a little bit of elevation here in the water. So there's a little pressure difference, high pressure here, low pressure there, pushing the water forward. The length is whatever that is, 9 inches. And the water is water, so it's got a certain viscosity. But the diameter here is small. Okay? Let me double the diameter. So I'm only going to increase the diameter by a factor of 2 between this capillary and this capillary. Huge difference. So that's approximately that factor of 16 I told you. Getting fluids through narrow hoses is very tough. Double the diameter, you get a whomping increase in the flow. I'm going to let this guy dribble away for the rest of the hour. Is that okay? Could do. All right. I mean, where does this matter? This matters like another piece of plumbing that we all care about is our arteries. You want blood to flow nicely through your arteries without much trouble, not needing a big pressure difference to drive it. If you narrow your arteries by a factor of 2, partly by bad luck, partly by diet and everything else, the flow through, all else being equal, drops by a factor of 16. So it's a big effect. So this is why it doesn't take very much blockage in the plumbing of our bodies to have a big effect on the fluid flow in our bodies. Another place where this shows up is in the plumbing of a house. As minerals build up in the various pipes, I don't know, do they build up so much inside houses with plastic pipes, which is the modern stuff? Certainly in the old days, the metal pipes and stuff, it was very easy to have a fair amount of crud build up inside the pipes. This building, for example, has a lot of crud built up in the inside of its pipes. So you lose a factor of 2 in effective diameter of the pipes. You lose a factor of 16 in the water flow. Big effect again too. Okay? Any questions about this? This is so fluid flow. Second thing to look at. So shifting gears seemingly completely. When fluid flows through a pipe, and actually, I do want to show you this. And let me ask this. I'll do this as a question. I'll make you guys pull out your little gadgets if you got them. If you just open a hose, you've seen this with a garden hose. You open the faucet moderately open. You just let the hose water come cascading out the end. It has enough energy to travel upward. Typical water. How high would it go? It's about 7 atmospheres. It should be able to go up 200 or 300 feet, and yet it doesn't. You know, where did the ordered energy go? You know. All right, I'll give you 5, 4, 3, 2, 1, 0. Yeah, it's the whole trip. And the issue is when you let the water flow freely out of the hose, you're letting it sort of go as fast as it can. It can't go, it negotiates. It tries to go too fast. It's got a lot of energy up initially. It tries to go too fast. It rubs too hard. Remember, the forces, the viscous forces increase with speed. So the faster it moves, the more it's being pushed backwards by viscous forces acting on it. So it kind of negotiates until it's going as fast as it can without actually coming to a stop and then not flowing at all. So it settles down. And the result of this is, I guess I should stop this because I want to play with more water. Oh, there. This effect. The water, at the water company, they packed it full of energy per drop. But it doesn't have very much energy when I do this. It's coming out, it's not very high. It's on the second floor of this building, which is something, but you know, it's not 200 feet in the air. It's at atmospheric pressure here. It's out in the open. And it's barely moving. It's got no big speed. And I guess I'm now realizing that I've had the camera misdirected all along. I can keep doing this. Undo the camera. My usual, never remember. So where did all the energy go? It became thermal energy because the water is rubbing the whole way. It's basically optimized its situation so it's rubbing just enough. It's rubbing just enough, but not so much it stops. It makes it out, but it's just wasted the vast majority of its energy. And I can then ask another question, which is this one. So what happens if I put my thumb over the end that I was just showing you? And does that increase or decrease the net amount of water that comes out every second? You know, so in which situation, covered or uncovered, is the most water coming out? 5, 4, 3, 2, 1, 0. So the majority is voting for you're getting more water out when the hose end is uncovered. And that is true. That is the right way. But a fair number of you are going that when you put your thumb over the end, you're getting more out. And that's tempting because the water comes out so fast. It's such high speed. And that's the point of this story here. So I'm trying to build a story. That if you take the water that's coming out right now, I left it running, wasty guy I am. So the water has gone up to as high a speed as it can get to without slowing so much during the rubbing process that it doesn't actually manage to get out properly. So anyway, this is about as much water as we can get out of it in this circumstance. If I put my thumb over it, I slow down the water flow everywhere in the hose. Oh, of course, it blew the plumbing off. So I'm slowing it down like crazy, but now I can spray the water across the room. It was, how did that happen? So that's the point of the story, is when you put your thumb over the hose, which surely you've done, the faucet, you have pinched off the flow so that not very much water can move through it per second. It has slowed down all the way to the water company. And because it's traveling slower now, it is rubbing less. And it is wasting less of its precious ordered energy as thermal energy. So it makes it to your finger. There's less water reaching your finger per second. But it reaches your finger having wasted less of its energy per drop. It's got the pressure still. It hasn't dropped, thrown that away. So that right before your finger, the pressure is back to almost the pressure the water company provided with its pump. And in that last instant of going from high pressure before your finger to atmospheric outside your finger, it's going through a nozzle. And it converts its pressure potential energy into kinetic energy. And it had lots of pressure potential energy before. And it ends up with lots of kinetic energy after. So let me say it one more time and then ask me if things aren't clear. By slowing down the flow, pinching it off, you manage to allow it to travel slowly, waste less of its energy coming to your hand. It comes to your hand, not as much per second, but it's still there. But every drop has a lot of energy left in an ordered form, as pressure potential energy, and then it squirts out like crazy through the little nozzle that you make. Is that okay? Any questions about it? A phenomena that at least when I was in college, we certainly experienced this, is when dormitory toilets often are the power flush ones. When you trigger them, a huge rush of water carries the water down, right? And when that happens, you learn to jump out of the shower quickly because you're about to get scalded. I hope this is familiar to some of you. Still, is this familiar? Anybody? Right? Why does this happen? It's because when the toilet flushes and it's connected to the cold water, when it flushes, the speed of the flow through the cold water plumbing skyrockets briefly. Huge amount of water flows through. It's like taking your thumb off the faucet. The water goes faster and it loses ordered energy. So the ordered energy per drop in the cold water line drops. And associated with that is the pressure of the water before your shower in the cold water line. The cold water pressure feeding the shower drops. And the hot water begins to win. It's it's not a battle, but the hot water keeps flowing as normal, unaffected. The cold water flow suddenly decreases. And you're about to get blasted. When you hear the flush, you're about to get blasted by hot water. All right? You got the physics okay? It's one of those things that modern technology can fix all this stuff and ruin I wouldn't say the fun, but ruin the experience. All right? It was definitely an experience in my day. Okay. So on to flows through a hose or pipe that's not straight. If the hose has a bend in it, something interesting happens as the water flows through it. So let's take a hose, nice simple hose, heading off straight, and we'll put a bend to the right in the hose. And when you do that, the water enters and exits still like normal. You just let the water flow. You've got no nozzle on the end, just the water's coming out. And yes, we can worry about the viscosity wasting some of its energy, but let's not, it's a minor effect in my story here. The issue is, as the water gets to the bend, it has to accelerate around the corner, right? Objects don't go, water doesn't go straight. Water tries to go straight because that's what inertia has in mind, right? Things don't arbitrarily turn, willy-nilly turn of their own volition. They have to be pushed because that's an acceleration. So for me, walking to your right and then turning toward you, I had to be pushed for that to happen, right? Because otherwise I would have gone straight. Same with water. If water's heading to your right and it turns toward you, something pushed it. That's really what I wanted to say. What's the something? Well, if it's right on the outside of the flow, where the wall of pipe is, we can say the pipe did it, the hose did it. If it's in the middle of the flow, the only thing that can push on it is more water. So the water to its left and its right must have conspired to push it, to cause it to bend toward the right. The pressure on its left and its right must have been different. And that is true. That when water flows around a corner in plumbing, and we'll make it horizontal so there's no issue of gravity messing stuff up. When water flows around a corner, the pressure, it develops a pressure gradient. It develops uneven pressures. And I'm going to do a rare occasion where I'll show you one of my slides. I mean, these slides are online. Here's the slide. This is an image that's also in the book. And one of these days I'll animate it. I just never gotten around to doing it. It's not a trivial animation. One of these is a laser pointer. Come on, laser pointer? Somebody? No. Okay. Here's water flowing. We're looking down on the hose. It's flowing this way around the bend to the right. And for these are the streamlines that I keep talking about. Here they are actually drawn in ink. And so the streamlines are nicely evenly spaced here, entering, and they're evenly spaced exiting. And actually the blue color is an indication of pressure and indicates that it's sort of the middle of the rainbow spectrum, and it's sort of normal pressure. Just some simple, nice, moderate pressure. Anyway, the water is flowing in like this, and it's going around the bend. For that to happen, it has to be pushed, and it's pushed by a gradient in pressure. And what develops, and has to develop, is high pressure on the outside of the band and low pressure on the inside. So there's a pressure gradient. Remember, fluids accelerate from high pressure to low pressure. So they accelerate away from the high pressure toward the low pressure on the inside. They accelerate toward the inside of the turn. That's the classic direction of acceleration whenever anything goes around a turn. When you're running along, you're on a roller coaster, on a carousel, you always accelerate toward the center of the turn, give or take, somewhere over in there in the middle of the turn, the inside of the turn. And that's what happens. You develop high pressure on the outside. And in my standard approach in the book is to go to the violet end of the spectrum is high pressure. And on the inside of the turn, you go to the red end of the spectrum, of the rainbow spectrum. That's low pressure. So there's high pressure on the outside of the turn, low pressure on the inside of the turn. Those pressure variations across the flow are real. You can drill a hole and you go in there with a little pressure meter. It's actually high pressure on the outside, low pressure on the inside. That's what's pushing the fluid and making it bend its path. You might wonder, where does that high pressure on the outside come from? Well, you can think of it as when you first turn the water on and it hasn't filled up yet. The hose isn't all assembled yet. The water enters here. It tries to go straight. It slams into the outside of the outside turn part of the hose. When it hits there, the pressure rises up as it pushes, and the hose says, no, you can't come here. I stop you by pushing. So the pressure surges upward here, and it stays up there forever, somewhat elevated. And this ends up, this inside of the turn, the water was trying to go by and not go there at all. And eventually it does go there, but it never, it always has a low pressure as a result of trying to bypass that spot. It's me waving my hands, trying to give you a simple explanation of that. So there's low pressure on the inside of the turns, high pressure on the outside of the turns. And this shows up in all kinds of situations, apart from just water in a hose. Yeah, I'll show you one. And this might be a little exotic for the moment, because I'm not going to do it in the hose, I'm going to do it in the open air. I'm going to spray air across the top, kind of a mound here. There's a curved piece of glass here with a hole in the middle. And as I blow air across this, the air is going to make an arc like this. So the air, I'd go on the side with the chalk, but that'll make screeches. The air is going to turn. The reason why the air actually follows that curve, we don't have to worry about right now, but it's a curve toward this. This is sort of the center of the turn somewhere here. That's going to be the lowest pressure in the story, inside that tube. Outside here, this is atmosphere, atmospheric pressure. This is going to be less than atmosphere. As the air makes that turn, like that turn up there. Is that okay? That low pressure in here is going to act as a suction, like somebody sucking water out of a container down below. It's like a drinking straw. And the water is going to go up. It's going to be pushed up by atmospheric pressure here into that pipe, into the low pressure that's created by the airflow over it. Any questions about the airflow? So here's the airflow. I'm going to get this going, blowing some air. And I'm going to blow it across that curve with a hole in the middle. Ah! That's pretty fun. All right. It's a snake! Ah! All right. You ever seen anything like this? It's a paint sprayer. This is how paint sprayers work. That suction that you get by making the air curve. Yeah, I'm tempted to release this guy again. It's sucking the water up. If it was paint, of course, we'd be spraying paint. But all the little air brushes, big paint sprayers, perfume sprayers, the moisture for the opera singers, la, 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 it's blowing air across that dome and creating a low pressure in the inside of the curve. Is that okay? All right. Just to show you another possibility, this is a more elaborate set of bends. This is flow entering from the left, flowing through here, heading toward the right, and as it necks down, this is a nozzle. The bends involved create a weird pressure variations until finally, in steady state flow, when everything settles down, we go from high pressure at the start to low pressure at the end. We've drifted toward the red end of the spectrum, the rainbow spectrum, which is low pressure. Pressure has plummeted. The speed of the fluid has increased. Incidentally, in these kind of drawings with streamlines, you can tell how fast the fluid is flowing at a particular location by how tightly spaced the streamlines are. The farther apart they are, the more leisurely the flow is, because it's sort of spread out. It hasn't necked down. Here, as it necks down to go through that narrow nozzle, it has to speed up. The streamlines get closer, and the pressure plummets. And actually, this is the origin of a truism that you may well have heard, that high speed air or flow or whatever is low pressure. That truism is only true in a certain context. if you make a flow of fluid speed up as you do in a nozzle, the way it speeds up is by using its pressure potential energy. So its pressure drops. So in the context of you're watching flow along one streamline, as the flow speeds up to go through a narrow neck, for example, its pressure drops. In that case, then you get high-speed air that is low pressure because you've traded pressure potential energy for kinetic energy. This nozzle effect, I can show you some of those too. That drop in pressure that occurs inside a nozzle. Two examples, and I'll save turbulence for next time. I don't want to use gas, natural gas. It's tempting, but I'll burst into flames. All right. Here's air. So I've got air coming out of the funnel. Right now it's just getting wider. It's not narrowing at all. In fact, that's a diffuser. That's the opposite of a nozzle. But if I make it fight to get around a ping pong ball, the ping pong ball now is making a very narrow region where it's almost touching the top of the funnel. In that very narrow spot, I'll turn this off because it's irritating my ears. In that very narrow, is it an annulus around there? That narrow neck, the pressure drops. And drops actually below atmospheric pressure. One of the phenomena of fluid flows is atmospheric pressure is often nothing special. You can go below it. We went below it here, went below it there, and we'll go below it here too. When you make the air speed up along a streamline again, it trades its pressure potential energy for kinetic energy, and it often ends up with pressure potential energy with pressures below atmospheric. So here's another open-end pipe. So the air is roaring out of there. Probably have to go a little faster. Okay, and if I force it to go between this plate and this plate, it has to go very fast. It's narrow. It's like going through the neck of a nozzle. Got to go faster. More air. All right. They're stuck together. They're stuck together by the low pressure between the two surfaces created by having the air have to squirt through that narrow neck and use a lot of its pressure potential energy as kinetic energy. And so the pressure is below atmospheric in that area. Okay? So I'll look at turbulent flow, sort of the third part of this more complex flows on Wednesday.